Welcome to this presentation. In this presentation, let's have an insight of TCP Congestion Control. So, in the previous module, we discussed about TCP, and now let's discuss about how TCP uses congestion control to avoid congestion and alleviate congestion in the network. In the previous model, we talked about flow control and tried to discuss the solutions when the receiver is overwhelmed with data. We said that the sender window size is determined by the available buffer size in the receiver. In other words, we assume that it is only the receiver that can dictate to the sender the size of the sender's window. We totally ignored another entity here, the network. So if the network cannot deliver the data as fast as they are created by the sender, it must tell the sender to slow down. In other words, in addition to the receiver, the network is a second entity that determines the size of the sender's window. Today, the sender's window size is determined not only by the receiver but also by the congestion in the network. The sender has two pieces of information: the receiver advertised window size and the congestion window size. The actual window size of the window is the minimum of these two. That is, actual window size is equal to minimum of RWND and CWND. RWND is nothing but the window size in the receiver side, and CWND is the congestion window size. And TCP's general policy for handling congestion is based on three phases. One is slow start, congestion avoidance, and congestion detection. So in the slow start phase, the sender starts with a very slow rate of transmission but increases the rate rapidly to reach a threshold. When the threshold is reached, the data rate is reduced to avoid congestion. Finally, if congestion is detected, the sender goes back to the slow start or congestion avoidance phase based on how the congestion is detected. One of the algorithms used in TCP congestion control is slow start. This algorithm is based on the idea that the size of the congestion window starts with one maximum segment size. The MSS is determined during a connection establishment by using an option of the same name. The size of the window increases 1 MSS each time an acknowledgement is received. As the name implies, the window starts slowly but grows exponentially. To show this idea, let's have an example. For example, say we have used three simplifications to make the discussion more understandable, and we have used the segment numbers instead of byte numbers, as though each segment contains only one byte. So we have assumed that RWND is much higher than CWND, so that the sender window size always equal to CWND. And we have assumed that each segment is acknowledged individually. The sender starts with CWND is equal to 1 MSS. This means that the sender can send only one segment. After receipt of the acknowledgement for segment 1, the size of the congestion window is increased by 1, which means that CWND is now 2. Now, 2 more segments can be sent. When each acknowledgement is received, the size of the window is increased by 1 MSS. When all 7 segments are acknowledged, CWND is 8. So if we look at the CWND, at the size of the CWND in terms of rounds, that is acknowledgement of the whole window segments, we find that the rate is exponential. For example, at the start, CWND is 1. After round 1, CWND is 2 power 1 is equal to 2. After round 2, CWND is 2 power 2, which is 4. And after round 3, CWND is 2 power 3, which is 8. And we need to mention that if there is a delayed acknowledgement, the increase in the size of window is less than power of 2. Slow start cannot continue indefinitely, and there must be a threshold to stop this phase. The sender keeps track of a variable name called SS threshold, that is slow start threshold, and when the size of the window in bytes reaches this threshold, slow start stops and the next phase starts. In most implementation, the value of SS thresh is 65,535 bytes. And the next problem is congestion avoidance, so which uses the principle of additive increase. If we start with the slow start algorithm, the size of the congestion window increases exponentially. To avoid congestion before it happens, one must slow down this exponential growth. And TCP defines another algorithm called congestion avoidance, which undergoes an additive increase instead of exponential one. When the size of the congestion window reaches the slow start threshold, the slow start phase stops and the additive phase begins. In this algorithm, each time the whole window of the segments is acknowledged, the size of the window, congestion window is increased by 1. To show this idea, we apply this algorithm to the same scenario as a slow start. Although we'll see that the congestion avoidance algorithm usually starts with the size of window which is much greater than 1. So in this case, after the sender has received acknowledgements for a complete size of segments, the size of window is increased by 1 segment, right? So if we look at the size of the CWND in terms of rounds, we find that the rate is additive. As you can see at the start, CWND is 1. After round 1, CWND is 1 plus 1, which is 2. After round 2, CWND is 2 plus 1, which is 3. After round 3, CWND is 3 plus 1, which is 4. So in the congestion avoidance algorithm, the size of the congestion window increases additively until congestion is detected. And the third category is congestion detection, which is multiplicative decrease. So if congestion occurs, the congestion window size must be decreased. The only way the sender can guess that congestion has occurred is by the need to retransmit a segment. However, a retransmission can occur in one of the two cases: when a timer times out or when 3 acknowledgements are received. In both cases, the size of the threshold is dropped to 1/2, which is a multiplicative decrease, and most two TCP implementations have two reactions. If timeout occurs, there is a stronger possibility of congestion. A segment has probably been dropped in the network, and there is no news about the sent segments. In this case, TCP reacts strongly. It sets the value of the threshold to 1/2 of the current window size. It sets CWND to the size of one segment. It starts the slow state phase again. And if 3 acknowledgements are received, there is a weaker possibility of congestion. A segment may have been dropped by some segments after that may have arrived safely since 3 acknowledgements are received. And this is called fast transmission and fast recovery. And TCP has a weaker reaction, that is, it sets a value of the threshold to 1/2 of the current window size. It sets the CWND to the value of the threshold, and it starts the congestion avoidance phase. And in summary, we can summarize that the congestion policy of TCP and the relationship between the 3 phases. We assume that the maximum window size is 32 segments and the threshold is set to 16 segments. On the slow start phase, the window size starts from 1 and grows exponentially until it reaches the threshold. After it reaches the threshold, the congestion avoidance procedure, that is additive increasive procedure, allows the window size to increase linearly until the timeout occurs or the maximum window size is reached. And the timeout occurs when the window size is 20. At this moment, the multiplicative decrease procedures takes over and reduces the threshold to 1/2 of the previous window size. The previous window size was 20 when the timeout happened, so the new threshold is now 10. TCP moves to slow start again and starts with the window size of 1, and TCP moves to additive increase when the new threshold is reached. When the window size is 12, a 3 acknowledgement event happens and the multiplicative decrease procedures takes over again. The threshold is set to 6 and the TCP goes to additive increasive phase this time, and it remains in this phase until another timeout or another 3 acknowledgements happen. So congestion in a frame relay network decreases throughput and increases the delay A high throughput and low delay are the main goals of the frame relay protocol. Frame relay doesn't have any flow control. In addition, frame relay allows the user to transmit bursty data. This means that a frame relay network has the potential to be really congested with traffic and thus requiring congestion control. For congestion avoidance, the frame relay protocol uses 2 bits in the frame to explicitly warn the source and the destination of the presence of the congestion. So the backward explicit congestion notification, that is BCN bit, warns the sender of the congestion in the network. You may ask now how this is accomplished since the frames are traveling away from the sender. In fact, there are 2 methods. The switch can use response frames from the receiver, or else the switch can use a predefined connection to send the special frames for the specific purpose. The sender can respond to this warning by simply reducing the data rate. And the next bit is forward explicit congestion notification. FECN bit is used to warn the receiver of the congestion in the network. It might appear that the receiver cannot do anything to relieve the congestion. However, the frame relay protocol assumes that the sender and the receiver are communicating with each other and are using some type of flow control at a higher level. For example, if there is an acknowledgement mechanism at this type of higher level, the receiver can delay the acknowledgement, thus forcing the sender to slow down. Thank you.